Okay, good afternoon, everyone, and sorry about the delay. Thank you very much for inviting me to deliver this speech about power transformer. I would like first to thank the organizing committee, the head of department, Dr. Didit, and of course, Professor Ashari for inviting me to deliver this short speech. The speech is about power transformer, and as you know, that power transformer is a very important piece of equipment in any transmission or distribution network. Any fault happens within the power transformer, it will not only lead to a lot of cost and loss of revenue due to business interruption and the stop of the power supply, but it may result in catastrophic failure, including fire, oil spillage, and environmental hazards, like what you are seeing now, which happened in many places around the world. The power transformer itself is a very complex piece of equipment, which has many components, including the winding, active winding, low voltage and high voltage winding, the bushing, tappet changer, which is the only mechanical part in the transformer, which changes the turns ratio between low voltage and high voltage, and the insulation system, which has paper to keep the mechanical integrity of the transformer, and oil. According to a recent survey conducted by a Segre working group, they found that about 38% of transformer failures is attributed to the winding of the transformer, low voltage winding and high voltage winding, followed by the mechanical part, which is the online tappet changer, and then the insulation system and bushing. So it is very important to keep eye on these components and these parts in the transformer. And if there is any fault we can find during the maintenance or during the condition monitoring, we have to rectify it as soon as possible to avoid catastrophic failure like the fire you have seen in the previous slide. So researchers and industry experts came up over the years by various diagnostic techniques, which can be categorized into chemical techniques, electrical methods, mechanical methods, and some special testing. And each of this technique is responsible to find the condition, health condition of the transformer from certain aspects. For example, the frequency response analysis here is responsible to detect any mechanical deformation in the core or in the winding. As you know, we don't have window to look inside the transformer and see what's happening inside. So frequency response analysis is one of the techniques that can discover the mechanical integrity of the transformer externally. Okay. A common challenge now in all of these techniques is the cost of monitor. Some of these techniques are very expensive. The reliability of electronic equipment, you have some sensors that you should connect to the transformer in a harsh environmental and operating conditions. You have very heavy electromagnetic field in the substation, background noise, high voltage. So how can we assure and guarantee the reliability and the accuracy of the equipment and sensor we are using? The performance of the sensor also under such harsh environment. And also the main challenge here is some of these techniques must be conducted offline. You have to take your transformer out of service, which will cause interruption to the power supply. So can we come up with online techniques? That's the main challenge in either research or in industry practice. So today I will only talk about one technique because of the time constraint, which is the frequency response analysis. In my talk, I will go through the principle first, the current industry practice, the challenges in the current industry practice, and how, as researchers, how we can overcome such challenges. That will be the scope of my talk today. So back to the principle, we know that the power transformer, including the core, winding, and insulation system, can be represented by equivalent electrical circuit. And this circuit will comprise resistive component and inductive component, representing the main winding, which is from copper or aluminum, and the insulation system, which is paper and oil, will be a capacitor and conductance. So that's the equivalent circuit of the transformer in high frequency domain. That's one disk or one turn only. So I put some animation here just to follow me. We start by the low voltage winding, which can be represented by a series inductive elements, R and L. And because this winding has insulation paper between them, so the insulation paper can be simulated as a dielectric capacitor shunted by dielectric conductance. Similarly, we have the high voltage winding, which can be represented by inductive elements shunted by dielectric capacitance and conductance. You know, in transformer, we have first the core, then low voltage winding, then insulation, paper insulation and oil, and then the high voltage winding. So between the low voltage and high voltage, we have paper insulation mainly, and oil going in ducts, which can be represented by capacitors and conductors. Between the low voltage winding and core, when we wind the transformer, we start by the core, then low voltage winding. But between low voltage winding and core, of course, we must have insulation, that's varnish on the laminated steel, and paper insulation. Again, any insulation can be represented by a capacitor. And all of these windings are immersed in oil. So the oil can be represented by a capacitor and dielectric conductance. So that's the equivalent circuit of a simple disk or turn. Okay? Frequency response analysis came from this equivalent circuit. We have capacitive component, we have inductive component, which is our frequency dependent. Remember, XL equal omega L, XC equal to 1 over omega C. So any variation in the transformer winding, whether the transformer is moving up, down, on the right-hand side, on the left-hand side, due to any reason that I will explain later, that will affect the capacitance and mutual and self-inductance, right? If, for example, refer to the basic formula for capacitance, epsilon A over D. So if you change the distance between two terms, that will change the capacitor. And that will affect the spectrum, the spectrum, frequency spectrum of the transformer. That's what we call frequency response analysis signature. So the technique, the measurement itself is very easy and simple. Anyone can do it. But you have to take the transformer out of service because you have to scan the transformer in right frequency range. You can't perform the test at the power frequency, 50 or 60 hertz. You need to detect inductive components, which can be detected at low frequency range, as well as capacitive components, XC equal 1 over omega C. That would be detected at very high frequency. So the typical frequency range for the test would be from very low frequency, like 10 hertz, to very high frequency, 2 megahertz. And that's why you have to take your transformer out of service because you need to inject variable frequency to the transformer. And then you scan each phase of the transformer, phase A, phase B, phase C, with this small device. The device is called frequency response analyzer, which injects very low voltage, 10 volt only. But the voltage here is of variable frequency from 10 hertz to 2 megahertz. And you measure the impedance or admittance or the transfer function of each phase against the frequency. That's called the frequency spectrum or characteristic of each phase. But again, back to the normal, what we expect when we measure, how the signature will look like. Back to the fundamentals, if we have RLC circuit, you know that XL, the inductive reactance is a straight line, omega L. The capacitive reactance is 1 over omega C. And if they are equal at a certain point, that will give us a minimum impedance, which we call a resonance or resonant frequency. and the corresponding angle will change from minus 90 to 90 degree, representing the inductive and capacitive effect, right? On the other side, if we have a parallel branch of our LC circuit, that's the susceptance 1 over X for the inductance and 1 over XC for the capacitance, capacitive susceptance. When they're equal at a certain point, they will give us maximum impedance, and that's called anti-resonance frequency. Also, that the angle here will be from plus 90 to minus 90, reflecting the effect of L and C. So what do we expect if we have very complicated circuit? I showed you only one disk, the equivalent circuit of one disk. If we have multi-disks like this, of multiple series and parallel branches, we expect multiple resonance and anti-resonance points. And that's what you will get in practice. You will get a signature like this. The x-axis here represents the frequency from, as you can see, 10 hertz to 2 megahertz. Y-axis here could be impedance, could be admittance, or could be transfer function, as in here in dB. And what you are seeing here are the frequency response of the three phases, phase A, phase B, phase C. So when you measure it, what to do with this? We have to compare it with the fingerprint. So ideally, when we have any transformer installed for the first time, we have to measure the frequency response analysis, and we call it a signature, fingerprint, like your fingerprint. And then in the future, if we suspect that the transformer has something wrong inside, in the mechanical point of view, we have to compare this signature with the previous one. But for all the transformers, especially in Indonesia, we don't have a fingerprint because the technique is relatively new. It's about 10 years old or 15 years old. So for all the transformers, when we don't have the fingerprint, we can just compare the three phases together, because we expect that the three phases are identical and will give us a similar response. So if you look here at phase, the white, yellow, and the blue, they're almost the same in the high frequency range. Maybe in the low frequency range, one of them is a little bit different, deviated to the left of the frequency response. And this one is the middle phase, phase B, which has different flux, magnetic flux, than the outer limbs. So this one is normal. And we can say that this transformer is healthy, nothing wrong with it. But when you look at another signature, this one here, of course, here, even if you don't have any experience with the frequency response analysis, you will observe that one of them is significantly deviated from the others in the low frequency range, which means that this transformer has something wrong in this phase. So what we have to do is to take the transformer out of service and unwrap the winding. So the suspected winding was this one here. So we have to take it outside to the workshop and take the papers out, unwrap it. Look, when we started to unwrap it, we found carbon tracking here spots, which means something happening inside. There's a sustained arcing or partial discharge underneath. And when we complete the unwrapping the winding, we found that was the static shield of the high voltage winding was loose. And that was the cause for sustainable arcing or partial discharge. The transformer looks normal and was working normal during the operation. But if you leave it, you may end up by having fire. If you don't notice that there's something wrong like this arcing or sustainable arcing may lead to fire, catastrophic failure. If we look at another example, this transformer, you know now the three phases here are similar to each other. The one to the left here is the middle phase, which is normal. So this transformer is healthy, nothing wrong with it. But if you look at this one, we have significant deviation among the three phases of the transformer, which reveals significant problem here in at least two phases. So when we took the transformer out of service, I don't think you can observe. Can you see that this very strong electromechanical fault happened inside the transformer? You know, when we have a short circuit fault, the short circuit current can interact with the leakage flux, phi, and cause electromechanical force that may cause the transformer to move down, or to have buckling like this, forced buckling. You can see the buckling here. That's huge force. If you don't see it from there, I highlighted it here, but you can see it from inside. That's inside view. You can see it in here. Again, with such kind of fault, the transformer will look normal. You won't see that. But suddenly, if you don't notice that, you may lose your transformer, and it may lead to catastrophic fire. So that's the problem of such kind of faults. So what's the challenges in this technique? As I told you, the measurement is very simple, very easy, and anyone can perform it. But the technique is so far offline. So we have to take the transformer out of service, which will cause interruption to your grid. That's from the measurement point of view. Also, this device here is not very reliable for minor deformation. So when you have emerging faults such as started with very minor level, that device cannot detect it. So we have two problems. The first question is, as a researchers, can we come up with online technique? And the main challenge here, how can we have variable frequency up to 2 megahertz while your frequency in Indonesia is 50 hertz? The transformer must work at the power frequency, which is 50 hertz. That's the first question. Second question is, can we increase the measurement reliability and accuracy? That's the second question. And that's a good field of research for guys who are studying at any university. Also, from the analysis and interpretation, you may have noticed now we are relying on graphical interpretation like this. So yes, we can tell that something wrong, but what's the kind of fault, location of fault, type of fault, level of fault? That's the main challenge here. We don't have standards and codes for automatic and standard interpretation. So that's another challenge. But today I will just, because of the timing, I will only talk about the first challenge, the measurements, and whether we can come up with a new device that can measure it in real time or not. So that's the question I'm trying to answer in the next few slides. Is it possible to come up with online technique? The first one is, okay, what I need variable frequency. And we know that if I have lightning or thunderstorm, lightning has impulse signal like this. And this signal, mathematically, for those who are good in mathematics, is a difference between two exponential functions, which if I transform them into frequency domain, I will find them that it contains a lot of frequency that will be enough to draw and plot the frequency response signature. So the first thought from researchers is, okay, if now I have a transformer in operation and I'm in a place like Florida. Florida is famous by hurricanes and lightning and thunderstorm. Can I use the natural lightning as a source of frequency response analysis? So I will not connect anything, but I'm using the natural impulse coming from the environment. Some other people, like in Indonesia, if you don't have lightning, you may have a switching operation during transit. If you are connecting a capacitor or taking one load shedding, that will cause a transit in the system. And during transit, you will have impulse function or wave propagating in the system, including the transformer. Can I use it to plot the FRA? People in industry in Florida started to think about that, and they thought about this transformer. That's auto transformer, which with tab changer here, high pass filters, and they bought their devices and measurements and scopes in here. So they didn't connect anything. They just connected their scopes, and they tried to use the natural lightning impulse as a source for the FRA. So they don't have to connect it to external source. And they were successful to do that. Look at this one here. That's one phase only, by the way. What they draw here is the amplitude of the admittance against frequency. And this frequency is not coming from external source, artificial source. It's coming from environment because of lightning impulse signal. And they plotted it twice in 2 different weeks, and they found that this phase is healthy. By the way, this one here is the angular, from minus 90 to plus 90, and this one is the coherence or correlation coefficient. They also changed the tab changer. Remember, online tab changer, that to change the turns ratio. So they changed it and they measured it on tab 1 and tab 2. And they found that, yes, that it can detect the changes in the turns ratio. However, this technique is not very practical. For example, in Indonesia, you don't have lightning that much. You don't guarantee that lightning or any signal coming from natural switching operation will have enough energy or enough frequency components to plot the frequency response analysis signature. So this one is not practical and is not implemented anywhere. It was just an idea from this company. Some other people said, okay, how about if I connect during the transformer operation, I can connect impulse generator. I need only maybe 1 kilovolt or 500 volt for a few microseconds. So can I connect it to operating transformer and for each phase and to plot the FRA? So what they did, they connected impulse signal like this through impulse generator, and they measured the impedance again, or admittance, or transfer function against frequency. And we have done some of work, like we used this one here, which is a pulse generator. We connected it to the transformer, and we found that yes, it can plot the FRA. So what you see here is what we did using the impulse generator and the signature due to the small device offline test. So they are identical. So this technique can be very practical and can be used for operating transformer. We did a lot of work on that and to find out if we can detect all types of faults. So if you look here, we created short circuit winding. We created also what's called axial displacement. I will come to this point later, what axial displacement is when the winding moves downward. And we created, you can see it in here, that's called the buckling in 1 degree or more than 1 degree. And that's short circuit, how we created a short circuit. We just simply we short circuited some turns here. And through this technique, we could detect the fault, okay? But again, the question is, that's how we implement it in real time. We can measure the voltage through capacitor coupling sensor and the current through Rogowski coil. But the issue is no one like PLN in Indonesia may not allow you to inject a voltage of 500 or 1 kilovolt to their transformer, operating transformer. Even if the voltage here is for a few microseconds, they will be reluctant. So the feasibility of this technique, again, is a question. The last point, I know I may exceeded my time, but it's only 3 or 4 slides. The last point is, okay, how about if we work a power transformer? I mean, can we just exclude the frequency? So we are not looking here at a spectrum of very high range of frequencies. I will perform the test at 50 hertz, and I will draw it. I'll do it through measuring the voltage and the current of the transformer. The advantage of this technique is you can perform it at the power frequency, 50 hertz. So there is no need now to use external source or to disconnect your transformer. The other point is you can do it every cycle, which is 20 milliseconds if your frequency is 50 hertz. So what the idea came to me from this simple equivalent circuit of the transformer. You may notice that there's no capacitor here because I don't have high frequency. I will perform the test at 50 hertz. At 50 hertz, the capacitor is almost open circuit, right? 1/2 pi FC. So that's the phasor diagram we all know. And what I thought about is I will plot a phasor between V1 minus V2. That's the voltage difference between the input and the output of each phase against input current. Mathematically, that will be an ellipse. So when I plot the voltage difference of each phase against input current will be an ellipse like that. So my thought was, can I use this ellipse as the fingerprint for each phase? And if I have any deviation from this, either I have bigger area or rotated ellipse, can that be an indication for a fault? So that's a graphical illustration of the technique, very simple. All what I want to do is to measure the difference of the voltage against the input current. So in each cycle, so for each one cycle like that, I will detect the current and voltage and plot the ellipse in 20 milliseconds. So we started this research by using finite element analysis that you can emulate physical systems using this software analysis. And we simulated turn-to-turn short circuit, like you can see the animation, please, here. So we short-circuited some turns to create this, and that can come through because of the insulation deterioration inside the transformer. You may have short-circuit. Disk deformation, because of the huge electromagnetic force that may be generated during faults, you may have deviation in the winding like this, the disks. We call it disk space variation or deformation. Leakage fault is coming from the oil. Look what will happen here if you lose the dielectric ability of the oil, you may have some leakage current coming from the winding to the tank outside. Axial displacement, when you have huge electromagnetic force on one winding, you have two components, one upward and one downward. If they are not equal, you may have a movement like that. Okay. Buckling, forced buckling, again, the electromagnetic force could be in radial direction, causing buckling like that. And you have seen that in the first 2 or 3 slides. Or radial deformation, when your internal winding here will move onward to the core, causing core deformation. So we have simulated all of these faults, and we found its impact on what we are proposing. So what we are proposing here is delta V against I1. And if I selected the first fault, turn-to-turn fault, starting from a healthy winding, we don't have any fault here. What will happen if I have fault? Look at this. The ellipse is rotating to the right and the area is increasing. How about if I increase the number of short circuit winding, the level of fault? The area is increasing further and rotating further to the right, increasing more if I increase the fault level. If I talk about a different one here, disk space variation, starting from the healthy one, if I have a disk space variation, we'll move to the right, but the area is not increasing here. If I increase the fault, rotating further, and so on. So this one is unique than the other one, is different than the other one, which give us a hope that the technique may work. For the next one, you can see here for axial displacement, starting from healthy, the area is not increasing, is not rotating either. But when I increase the fault, the area is decreasing. So this means the technique, I will skip this, the technique can discriminate between various types of faults. So that's how we discriminate in terms of the area of the ellipse and the rotation. So the technique is working in the first stage of our research. That's all of the faults at the same level. And you can see that starting from the healthy, the dotted one here, we have different impact from each fault on the ellipse. We have also done some practical measurements on a custom-made transformer in which you can have the winding outside. You can create a space deformation between the winding by taking these spacers out, or you can move it up or down or in radial direction. And we found that the practical results are almost typical to what we achieved in the finite element analysis. We have done that on even a bigger transformer, and we created a lot of faults, and you can see that it's similar to the impact in the simulation stage. However, again, the main point here is to standardize and come up with automated technique. So what we did, we came up with a software code based on the image processing. I'll talk quickly about this. So what we did, we started by measuring the geometrical features of the ellipse, including centroid, perimeter, internal area, major axis, minor axis, and so on. And we calculated the eccentricity. And the purpose here is, can we create a code so that I don't need any personal intervention here? So the code can tell me by what's happening directly. And that's a snapshot of the code we created. As you can see here, we are using image processing to compare the ellipse. And if there's any difference, it will tell me like this. It will give me a report. The difference in each parameter geometrical parameter and will tell me if there is any fault or not. For example, if they are similar like this, it will say there is no fault. In some cases, the code is confused and may give you two types of faults, that and or that. We took it to a commercial implementation. That's I'm finishing in 3 minutes. Commercial implementation. So we had this in a substation, and all what we need is access to the current, input current, and the difference between input and output voltage, which is any transformer should have this information. But if we don't have, we can come up with a data acquisition measurement like this, which we developed to measure the current and voltage at each side of each phase. And we have done that using a lab view, so that while you are in the control room, you can watch and see the sinusoidal waveform of each phase, voltage and current, and the proposed ellipse. Then if there's any deviation in the ellipse between one cycle and another, I told you that the technique can be performed every 20 milliseconds. The software code will tell you if there's any difference or not. Of course, the ellipse will be affected by the load. So if you change the load, the ellipse will be affected, but will be affected in a different way than what I showed you in the faults. In the faults, it was rotating and the area it was increasing. In this one, it's not rotating, but we came up with a mathematical technique to normalize it, so that the ellipse will be always like this by using this normalization, regardless the load variation. And hence, any change in the ellipse will be attributed to certain fault. I think I will stop here by that's to take home here by this very simple comparison of what I presented today. The current technique, current industry practice, is using frequency response analyzer, which is offline technique, is accurate, but it has two problems. The first problem is offline, you have to take your transformer out of service, and it's not very accurate when you have a very low fault level. The second one is it depends on personal expertise, which means you may come up with different conclusion for the same frequency response analysis signature, because it depends on the level of expertise of the person who is analyzing it. The online FRA using impulse signal can come up from natural switching operation in the network, or can come up with from lightning and thunderstorm. But this technique is not very practical, because you can't guarantee the environmental impulse signal to have enough energy and enough frequency spectrum to plot your FRA. And if you are using external impulse generator, people in utility like PLN may not allow you to do that for their operating transformer. The technique we worked on is called VI Lysiges, and the difference here is we are not conducting it at very high frequency. It's only at the power frequency, which is 50 hertz, and this technique can be conducted in real time. However, it is still in research stage. Thank you very much, and sorry again for the timing. Sorry. Thank you.
Okay, thank you very much, Professor Ahmed Abu-Siada. It is quite very interesting presentation regarding the how to detect the mechanical fault inside the power transformer. And because the time is quite limited, so I will allow only for 2 questions from the floor. Okay, maybe anyone? If you have a question, you can raise hand, or you can speak directly. Anyone, please? Yeah, because actually I have one question.
Yeah,
so
sure.
I will keep my question after the participant ask a question.
Yeah.
Anyone from the participant? Anyone has a question? Okay. Yes. It is from Mr. Nur Afandi. Okay. Please, you can ask to Professor Ahmed Abu-Siada directly, please.
Okay, Professor. Okay, thank you for the opportunity. My name is Afandi from ITS. For the online monitoring, the VI Lysiges pattern method, how if we only recognize the pattern of the voltage of the potential transformer in the power transformer. Maybe we can just recognize the pattern in some period and give a threshold maybe with a statistical method. If the pattern is outside the pattern we record before, we can call it an abnormal. Is similar like that or maybe any other?
You mean relying on the voltage signal only?
Yeah, maybe we can just use a voltage transformer on or the how to say power factor. We can maybe use that for the pattern analysis we record, and then we maybe we can use some technique like neural network, so we can record the pattern, and then we can analyze if in the further operation of the power transformer maybe there is an abnormal. We can compare the current situation with the previous recorded pattern. How if we conduct like that?
Yeah, that's a good question, but measuring the voltage only will not reflect the mechanical integrity or mechanical condition inside the transformer, because a change in the voltage profile or the voltage level can be due to any other reason. Could be due to the change in the load, it could be due to the change in the generation, or could be the change due to any other electrical fault, not a mechanical fault. So measuring the voltage only will not be helpful in revealing the mechanical integrity of the transformer. Similar power factor is, if you are talking about the electrical power factor, that is also can be changed due to the change in the load or a change in any other electrical component in the system. Why I selected both sides, why I selected V1 and V2 and the current here, because the area of the ellipse will represent the losses in the core, and these losses will rely on the mechanical deformation and the physical dimension of the transformer. That's why we selected both current and voltage to come up with the signal.
Okay, Professor. So we compare the characteristic of the input voltage and current, and then we analyze it with the output voltage and current of the power transformer, something like that. We analyze both pattern, input and output.
Yeah, you can do that, and some people have published something like that. Okay, they said, okay, why we need to plot the VI and get the characteristics, get the digital signal processing or digital image processing to analyze it. If I have the raw data, V and I, can I do the same? Yes, you can do that. But again, you have to correlate the input and the output. You can't just rely on individual values, V1 only or V2 only or I1 only or I2 only. You have to look at the full spectrum. I agree with you. And using the raw data, or you can use artificial neural network, as you said, or machine learning to give the reference or the range of normal operation. And if the values deviate from normal operation, you can report a faulty mechanical fault within the transformer. But that will not be very certain, but that's a technique and maybe simpler than the VI locus diagram.
Okay, thank you, Professor, for the explanation. Thank you very much.
Thank you.
Right, a very interesting discussion. Maybe now for the last question from the participant. Anyone with a question? Right, I haven't seen any participant raise a hand. So, Professor Ahmed, may I have a question for you?
Yeah, sure.
Okay, so I'm quite curious with this method because it's quite, it seems so simple, but it's quite very powerful because it can be done with online monitoring. So my question is, now most industrial, now they are using the nonlinear load. So what's the effect of the nonlinear current in this method? Does it reduce the accuracy or some yes, accuracy of the detection?
Sorry, Dr. Dedit, what you said? Nonlinear what?
Nonlinear load.
A nonlinear load.
Yeah.
Okay, that's again another good question. But if you look at if you look at the last slide, when I said that we normalize the load, I was talking about linear loads. Non-linear load, the impact here will be in the harmonics and the distortion that will cause to the voltage and the current signal. That will be seen in the signal. But using a digital filter in the code we created here, we used a digital filter to filter all the unwanted harmonic and background noise. So the nonlinear load is a very good question, but yes, that will affect it in terms of the harmonics and distortion of the signal.
All right, thank you very much, Professor Ahmed, for the answer. Because we are already running out of the time, so we have to conclude the first session of the Keynote speech. So please let us give the warmest applause for Professor Ahmed Abu-Siada. Thank you very much.
Thank you.
Okay, now, I will give the session back to the MC. Yeah, thank you very much.
Thank you.